तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Now, let us consider an example. Design a class A power amplifier for delivering 10 watt output into a load of 10 ohm. So, this is a typical design of power amplifiers. The RL is given as 10 ohms. Power output is given as 10 watts, and from our discussion earlier we had the configuration that has been chosen. This is 10 ohms, this is VCC. So, we know that VCC squared by 8 RL. Please remember that the maximum swing was VCC by 2, okay, and therefore, the peak voltage across the load was VCC by 2, and therefore, the RMS value of that voltage is VCC by 2 root 2, right. That squared, okay, VCC divided by 2 root 2, okay, V squared by RL is the power output. So, that is actually VCC squared divided by 8 RL. So, if you use a load of 10 ohms, therefore, VCC squared divided by 8 into 10 is going to be equal to 10 watts. So, the minimum value of VCC you should use. You can use higher value if you want, but then you are honestly wasting power. Okay. So, the VCC minimum can be obtained from this. VCC squared is going to be equal to 800, right. VCC squared divided by 80 is equal to 10 watts. So, VCC squared is equal to 800, or VCC is equal to root of 800, which is 400 into 2, that means 20 root 2, right, 400 into 2. So, 1.4. So, this is actually 28 volts. So, you can now see that supply voltage minimum is 28 volts, maybe you will fix it at 30 volts, right, see if you want it. So, this is the supply voltage. If this is taken as the supply voltage, this is equal to 28 volts. What is the quiescent current, we would like to know. So, VCC by 2, okay, is the quiescent voltage at this point, that divided by 10 ohms, that is going to be the IQ. Is it clear? VCC is already known as 28 volts by 20. So, you have to operate it at 1.4 amperes. So, in order to get 10 watts output, our quiescent current should be 1.4 amperes. Now, how to make it operate at 1.4 amperes? This 1.4 amperes flowing through 10 ohms will generate here, okay, 14 volts. That is understandable because 28 half of that. So, this 14. So, quiescent voltage here should be 14 point, let us say 7 volts. That should be the VBQ. Okay. So, we have now got VBQ. So, we have to put here a resistance arrangement R1 by R1 plus R2 from 28 volts, R1 by R1 plus R2 into 28 shall be equal to, okay, 14.7 volts. It's about almost half. R1 is very nearly made equal to R2 because this is 14.7. That is the situation. And if you know the beta of the transistor, this divided by beta, let us say beta is 100. So, 1.4 by 100, okay, is going to be about 14 milliamperes. So, 14 milliamperes should become small compared to the current in this. That means, you might have to at least spend about 140 milliamperes here. Okay. So, if beta is, let us say 100, this current is about 14 milliamperes. So, this current is about 14 milliamperes. So, this current at least shall be 140 milliamperes, let us say. You cannot make it much more than 140 milliampere because that will become comparable to 1.4 amperes. So, it is 1/10 of this, right, but 10 times this. So, you can see this. Therefore, R1 plus R2 28 divided by R1 plus R2 is equal to 140 milliamperes. So, R1 plus R2 is equal to 28 by 140 K. So, about 200 ohms. So, okay. From these things you can find out the value of R1 and R2. R1 is very nearly equal to R2, that means it is very near 100 ohms. Okay. This being slightly greater than 100 ohms, you can find out R1 and R2. I will leave it as an exercise for you from this. So, this is the complete design of my power amplifier. Now, I have to specify the transistor. The circuit is completed. Transistor T. $10 power is dissipated, actually speaking, in the output. What is the power input? Let us see. 28 into about, actually speaking, 1.4 plus 0.14. So, actually 1.54, okay, watts. That is the power input. Okay, how much? 43.1 watts. So, you can see that that is 10 watts, this almost 4 times that, right. Now, because particularly we have included other bias, these things, etc. So, it is less efficient than what we have considered. Best efficiency is 25%, right. So, less efficient than that. Then what is the power dissipated in the transistor? If 10 watts is the output power, you can see that the power dissipated in the 10 ohms, okay, is going to be power dissipate this 1.4 amperes is flowing through, okay, this 10 ohms and the transistor. So, the transistor voltage is 1.4 into, okay, 28 minus 14, that is 14 volts, right. So, 1.4 amperes, okay, into VCE. VCE is 14 volts. So, that is the power dissipated in the transistor. How much is this? 19.6 watts. The resistance dissipates about 14 watts, 1.4 into 10, 14 watts. So, 19.6 watts is the maximum power that is dissipated in the transistor under quiescent condition. 43.1 is dissipated overall, right, just to get 10 watts output signal power. So, the transistor has to be rated for 19.6 watts greater than. So, transistor power dissipation should be greater than 19.6 watts. Some 20 watt transistor or something like that you can select. The current, the maximum current through the circuit is going to be 28 volts, okay, divided by 10 ohms when this goes to VCC. So, that is maximum current, 28 volts divided by 10 ohms, which is 2.8 amperes. So, the current rating of the transistor should be greater than 2.8 amperes. So, something like 3 amperes or so the current rating. And voltage rating obviously is 28 volts. VCE max should be greater than 28 volts. So, these are the ratings of the transistor required. So, now the design is complete. You can therefore specify what kind of transistor is required here, put the circuit, and it should work satisfactorily. Now that we have seen class A power amplifier, how inefficient it is for delivering a power output of 10 watts, we had to spend something like 43 watts or so, totally inefficient. Now, we are coming to one of the most efficient power amplifiers existing today. This is covering 90% of the classical power amplifiers available to us. So, this is class B power amplifier. What we have discussed is class A power amplifier. What is class A? Class A says that if you have a transistor operating at 1 milliampere current, quiescent current, the current can change up to 0 milliampere to 2 milliamperes, that is all. If you have it operating at 2 milliamperes, it will change up to 0 milliamperes up to 4 milliamperes on the other side. Right. So, this tells us that transistor has to keep waiting with a quiescent current, constant current, and keep dissipating lot of power before it encounters the signal. This is not a very efficient way of doing it. Instead, we just mentioned last time also that the transistor will be permitted to sleep and is woken up only when the signal arrives, and that kind of operation is class B operation. That means transistor is off when the signal is not there, and signal itself makes it go to on state. Right. So, the transistor is now biased to be at off state. Let us say transistor is simply grounded here, or let us say, let us consider the same common collector stage. For example, how do we work this out? Normally, I connected it to VBQ. Now, I do not want to connect it to VBQ at all, it is just simply grounded, let us say. So, this is actually off, even though the load is still connected here. But then, the moment the signal comes, I will make the signal itself conduct, but the only signal that will conduct this transistor is positive going signal, that much I know, and that also it has to cross V gamma. This is called the cut-in voltage. So, if that is not a problem, because V gamma is only 0.7, my signal is going up to say 20 volts or 30 volts. So, I can just say that as soon as that value comes, it conducts. So, this is going to conduct only for positive going cycle. So, that means 1/2 of my sine wave, you can make this work. When this sine wave comes, the output will be a sine wave. There is no quiescent current is 0. So, the power supply is not delivering any power as long as the signal is not there. When the signal is there, it is delivering power. Let us look at it. If this is the way I want to amplify, only 1/2 of the sine wave, right? The other half I will take care of by using another transistor which is connected to minus VCC, let us say. So, that will be, if this is NPN, this will be PNP, and this will be connected to minus VCC, and it will be connected to the same input. So, that this can go both positive and negative. This is the famous complementary symmetry pair, PNP, NPN, PNP pair, class B. Necessarily, for class B to be operative, 1/2 of the waveform is to be taken care of NPN, the other half of the waveform is to be taken care of by PNP, both working on to the same load from the same input. So, this structure is one of the most popular structures because it does not need any biasing arrangement. Okay, signal itself is biasing it, and the quiescent dissipation is 0. Now, let us see the efficiency. Obviously, when one half of the signal comes, let us say this is going to V p, this is V p sin omega t, output is going to be V p sin omega t. It is a unity gain, one half being produced by N p n, the other half being produced by P n p. Now, of course, there is going to be a small amount of distortion. This is called cross over distortion. At the point of crossover, there will be small gap, because until the voltage reaches V gamma, none of the two transistors conduct. When it goes to V gamma, this will conduct. When it goes to minus V gamma or lower, this will conduct. So, in between, therefore, there is going to be some gap like this. If I exaggerate it, or if the peak voltage is low, you can see this, and this is called crossover distortion. Unlike other distortion, this distortion is more when the signal is small, and distortion is less when the signal is large. Other distortions are the other way about. When the signal is small, the distortion is less, and the signal is large, distortion is more. Whereas crossover distortion, when the signal is small, distortion is more, and signal is large compared to V gamma, the distortion is less. So, this crossover distortion is one thing that will come. We will see how we can get rid of this distortion, but this is a very useful configuration. Suppose it is something like full swing of 28 volts, etc. This crossover distortion will not be visible at all to you. And when you feed a sine wave with a peak amplitude of 28 volts, you will get a sine wave of 28 volts output or 30 volts output, depending upon the VCC. Suppose therefore, V p sin omega t is the input, we are now able to produce that output without much of a problem, let us assume. Now, let us try to find out what the output power is. Output power is V p squared, V p by root 2 is the RMS value, V p squared by 2 RL, V p squared by 2 RL. Always, if V p is the peak, V p squared by 2 RL is the output power. Now, as far as V p is concerned, in this case, let us say V p can go as much as VCC, and on the other side it can go to minus VCC. So, V peak is VCC maximum. So, maximum power output is VCC squared divided by 2 R. Let us keep that separate. This is power at any peak swing V p. This is the maximum power output, power input. This is very interesting. One half of the cycle, this conducts, and it will produce a current which is V p sin omega t divided by R L across the. So, this is the current waveform. Now, you have current waveform, half waveform current for this, and other half is giving to be for this. Now, only for half the period, if this is the period, for T by 2 each transistor conducts. So, this is going to be the current waveform into each of the supplies. Let us consider now what is the average current. If this is V p, average current, this is V p by R L, let us say peak. Average current is going to be V p by R L divided by pi. You know, for a half wave rectified sine wave, average is Vp by pi into RL. This we had discussed long ago in electronics rectifiers. So, this into Vcc is the power delivered by positive supply. This is the average current. This into Vcc is the power delivered by the positive supply. That again into another Vcc is going to be power delivered by the negative supply also. That into therefore 2. This power is going to be delivered by positive supply, and there is same power dissipated in the negative supply also. So, total power dissipated is 2 times that. So, this is the power input. So, we can now say that the power input in general is twice by pi Vcc into Vp by RL in general. So, what is efficiency? Efficiency is output power divided by input power. So, P out by Pi is equal to Vp squared by 2 RL, that is the output power. Input power is twice Vcc Vp, okay, by pi RL. So, efficiency is at any point, this is at any point, okay, efficiency is going to be pi by 4 into Vp by Vcc. What is therefore the maximum efficiency? Maximum efficiency occurs when maximum power output is got. Okay? You can see that because it is directly proportional to Vp by Vcc. When Vp becomes equal to Vcc, maximum efficiency is got. That is for maximum output power. So, maximum efficiency occurs for Vp equal to Vcc, that corresponds to P naught max, okay, and therefore, that is going to be equal to pi by 4. Very important relationship. Okay. What is pi by 4? Pi is 22 by 7, okay, 28 or 11 by 14. It's going to be point, so 0.78 or about 78% efficiency. This is the best possible efficiency you can think of for a class B power amplifier. That is when you are getting the maximum output power. So, it is always less than 78%. What it means is, if 20, let us say 78% efficiency simply means that the wasted power is only about 22%. 78.6. Okay. This is very useful to remember this, because it is nothing but pi by 4. Okay. 3.14 divided by 4. Okay. Now, I would like to point out something that is very important. This is not 100%. This is going to take close to 100%, very nearly 80%, right. but this is good enough. For most of the linear amplifiers, this power amplifier is quite often used. Now, therefore, let us see what is the power dissipation maximum required for the transistors now, because the transistors do not dissipate any power when the input signal is 0. Again, when the input signal is maximum, they will dissipate least amount of power, because most of the power has been transferred to the load. So, the transistors will dissipate power maximum only somewhere in between, not for the maximum drive. This can be illustrated mathematically also. So, what is the transistor power dissipation? We have to find out the maximum dissipation that is likely to occur in the transistor for the certain specific signal condition, and then put that transistor with that power dissipation or higher power dissipation there. So, let us see how to select this kind of transistor. P I is given as 2 by pi V C C V P by R. From that, this is the input power. Output power is V P squared by twice R. What is the power dissipated in the transistor? Output power is coming across this load, and input power is being taken from this. Entire power now is dissipated only in the two transistors. So, the power dissipated in the two transistors mind you, is going to be input minus output simply. So, power dissipated in the transistors is power inputted minus power output is 2 by pi VCC Vp divided by RL minus Vp squared by twice RL. So, this is the power dissipated in the what? Two transistors. This is, therefore, we can find out when this becomes maximum. So, we just simply differentiate this with respect to Vp. Vp is the variable. Delta Pd by delta Vp, if it is going to be maximum, has to be equated to 0. So, let us find out delta Vp Pd by delta Vp. So, this is 2 Vcc by pi RL here minus twice Vp by 2 RL. So, that should become equal to 0, and therefore, we get this condition Vp should be equal to twice Vcc by pi. This is the signal drive, it is not the full signal drive. Full signal drive corresponds to Vp equal to Vcc, it is almost 2/3 that. At that signal drive, output power is not maximum, but the power dissipated in the transistor, two transistors, is maximum. So, let us find out what that power dissipated is. So, the power dissipated in the transistors is, can substitute this Vp into this equation, and this is going to be equal to 2 Vcc by pi RL into Vp, which is 2 Vcc by pi, that means 4 by pi squared Vcc squared by RL minus 4 Vcc squared by pi squared RL by 2. Okay. So, 4 VCC square by pi squared RL minus half of that. So, it is nothing but half of this or 2 by pi squared VCC squared by 2 VCC squared by pi squared RL. That is the power dissipated in 2 transistors. So, power dissipated in one transistor equals half of this, which is 1 over pi squared VCC squared. 1 over pi squared is nearly 1/10. Pi squared can be made equal to 10. So, 1/10 of VCC squared by RL. You can see this VCC squared divided by 2 RL is the P naught max, maximum power output you are capable of getting from this arrangement of complementary pair with VCC here and minus VCC here is equal to VCC squared divided by 2 RL. Okay. So, if this is equal to let us say 10 watts, the same example let us say, if this is equal to 10 watts, okay, then VCC squared divided by 2 RL into 2. Okay. VCC squared by 2 RL is the output power maximum. Okay. 1/5 of that is what is required for the transistor PD max. That means 10 watt output power if you want, you have to have a transistor whose power dissipation ability is only 5 watts, 2 watts, 1/5 of 10 watts, which is 2 watts. So, if I want a 10 watt power, I have to have only transistors which can dissipate 2 watts. Consider this earlier situation when we had output power of 10 watts, okay, we had to have something like 20 watts, okay, for the maximum power dissipated in the transistors. Is that clear? So, this is the difference between class A power amplifier and class B power amplifier. Now, let us work out an example. Design a class B power amplifier delivering a 10 watt power into a 10 ohm load. So, the circuit configuration that we are going to select is the same thing, only thing is now this is the 10 ohm load and we have the complementary symmetry stage connected to VCC and minus VCC. This is the simple circuit. So, here we have to only find out what the specifications are for the 2 transistors, that is all the design is, and find out the value of VCC minimum that we should have for delivering 10 watt load into 10 watt power into 10 ohm load. So, we have earlier found out that the swing being VCC, right, VCC squared divided by 2 RL, okay, is the output power maximum, and that is given as 10 watts for a 10 ohm resistance. So, VCC is square root of 200, which is 14 volts. Okay. So, we have this already decided. So, the design is over except for the specification of the transistors T1 and T2. T1 is NPN, T2 is PNP. Okay. Now, when this is 14 volts, this can go to minus 14 or 14. So, the maximum VCE for each of these transistors, okay, should be greater than, okay, 28 volts. This is 14, this can go to minus 14, okay, and this can go to 14. At that time, this will have the maximum voltage 28 volts. Then IC max. So, either this will go to 14 when this conducts, or this will go to minus 14 when this conducts. So, in either case, the maximum current in these two transistors will be respectively 14 by 10 volts, which is 1.4 amperes. Should be greater than 1.4. So, compare this with earlier thing. Earlier also we needed a transistor, only one transistor with the same kind of VCE max, but we had a quiescent current of 1.4 amperes there, but the peak current was 2.8, double this. But these are shared now by the two transistors. At one time this conducts, at the other time this conducts. So, 1.4 amperes. And the power max, PD max, has to be greater than, okay, we have seen 2 by pi squared times P naught max, which is greater than about 1/5 the power 10 watts. So, 1/5 the 10 watts greater than 2 watts. So, these specifications, okay, this circuit will function satisfactorily. Now, let us come to the last topic of discussion in class B. The major problem in class B is the crossover distortion I pointed out. It is very efficient, okay, 78.6% efficiency, but distortion for low signal level is pretty high. That is because of the fact that the transistor, this or this, they do not have any bias applied here, and therefore, the cut-in voltage of, let us say 0.7 or 0.7 here, that must be crossed. So, that means actually speaking, right, when the signal comes, the signal itself, okay, is required to bias it first to a voltage which is greater than 0.7 and then start conducting. This makes it difficult to use signal drive here which is less than 0.7. If it is less than 0.7 signal drive, peak drive, output will not come here at all. The transistors will not conduct throughout. So, output will be 0. So, the extreme limiting factor is when the peak amplitude of the sine wave is of the order of 0.7, nothing comes at the output or less. So, what to do about this? For this, we do what is called pre-biasing. That means, we will put a voltage here which is, let us say, if 1.7 V gamma plus V gamma is equal to twice V gamma, that is required here is 0.7 plus 0.7 which is 1.4. We will apply here a voltage of 1.3 volts. Okay. Why? That is, it is just about to start conducting. The signal has to only come in and give a voltage of about 0.1 volts rather than this 0.7 on one side and 0.7 on the other side. So, to this extent we will bias this. how to do this biasing. So, this biasing can be done by using resistance now like this, one way of doing it. This is VCC, this is minus VCC, and this potential we want it to be ground potential. That means, if this is, let us say R1, this is R2, this is also R1 and this is R2. This potential will be 0, because this is VCC, this is minus VCC, and on either side of this we have R1 plus R2, okay, it is perfectly symmetric. So, this potential here is going to be ground potential. Is it clear? So, I can therefore connect the signal here. So, and provide adequate bias here, 0.7 on this side and 0.7 on this side. So, let us say this is about 0.7 here, 0.7 here across this. Then what will happen? The signal will appear, already there is 0.7 and this gets cancelled with this, that is required here. Okay. So, the signal when it comes to the base comes with the bias, okay, added on to it. So, that this moment this crosses 0, this transistor will start conducting. Similarly, the moment this goes below 0, this transistor will start conducting. This is called class A B operation. What does it mean? It is just, if it is 0.7 that is required, you might provide 0.65 and 0.65. So, that it is just about to start conducting. That means, the quiescent current is still not as much as the class A amplifier, but it is going to be there, small amount. 0.65 does not mean that there is no current, it is just that at 0.7 it really starts conducting. Okay. 0.65, the current is going to be extremely small compared to the current that is required for it. So, there is going to be some amount of bias current, such that that bias current into VCC is a small quiescent dissipation that is going to be tolerated in order to prevent this crossover distortion from taking place. So, this biasing is called class AB biasing. Now, it may be fairly difficult to find out the precise resistors here, okay, so that this is just less than what is required. Okay. For that purpose, what is done normally in integrated circuits is that you put here just 2 diodes, okay, so that you have 2 V gamma straight away provided, okay, for this to be biased. So, actually when there is some current flowing through this like this is still going to be at ground potential, and therefore, this is going to provide the V gamma cut in voltage for making this conduct straight away, and this is going to provide the minus V gamma that is necessary to make this conduct. Okay. If these diode and the transistors are made out of the same geometry, then this current is going to be the same as this current. This is nothing but a current mirror that I had earlier talked about. So, this current is going to be same as this current. The load current will be still 0, because this current is exactly same as this current. Load current is still 0, but you can make any quiescent current pass through the power amplifier, which is quite low. Okay. So, it is in readiness to conduct the moment the signal starts coming into picture. So, this kind of class AB biasing is what is normally adopted in power amplifiers, okay, to reduce the distortion. The price you are paying is that the efficiency is now going to be still much less than 78, because of the fact that there is some more quiescent power dissipated here. Earlier there was no quiescent power dissipated at all. Okay. Now, there is certain amount of small quiescent power dissipated here. That is the price you are paying to eliminate the crossover distortion.